Good afternoon, everyone. My name is Swastik Karka, and we are Team Arlington, the Mavericks. And this is my team. He's Slade Wang. He's a PhD student, and Imran, he's also a PhD student. The topic of our presentation is AI-empowered video analytics for preventive traffic crash risk identification. Let's look at the outline. So the outline is going to go like, we're going to have an introduction, then we're going to go with problem statement, the solution that we proposed, system overview, the cost estimates and timeline, and the anticipated impacts. Let's look at the problem statement. So what actually is a problem? So over here we know that it's not just the problem of our city, but it's an overall problem throughout the state that we have a good transportation system, but the thing is it's complicated, and things like we have a lot of crashes, near miss, which is unanticipated events that's going to happen. And a lot of fatal crashes are occurring, which is over 50% of a fatal crash occurs at intersections, therefore making it prone to high risk, and intersections are one of the worst places where chances for it to have a fatal crash is very high. And it creates a lot of loss of life, property damage, and increased emissions. So that's, and at the same time, intersection improvements are very costly, and it's not done, it's just, right now it's done in a way that whenever we see crash, okay, maybe there's a problem, let's fix it. But our solution is more of like, there should be a systematic approach of solving this problem. Therefore, in city of Arlington, they have been monitoring the traffic through ITS cameras, but those cameras have highly underutilized, and because of high privacy concerns and high storage cost, they're unable to utilize those cameras for any other aspect. Therefore, if you look at the data on the left-hand side, there's a heat map of crashes happening, and most of them are happening at the intersection. Last year it was 6,156 crashes, and this year nearly right at the moment more than 2,000 crashes already happened. It might be fatal and non-fatal. So we need to leverage the technology that our UT Arlington already have, and so we want to propose them a solution. The solution is to provide them AI-based solution, which will help them to detect near miss. And a lot of research said that a near miss is a good proxy for high crashes. So the places where there's high near miss, there's a high chance that they will have a lot of crashes as well. So the solution is to give them a software which is AI-empowered video analytics for smart transportation called AVAST. And why it is unique? It's because the transportation engineering domain-specific knowledge is not utilized in AI. AI can do a lot of stuff, like we can work in non-transportation related field, but the thing is, we are using the transportation-specific engineering-related space domain and utilizing it with AI to give or propose a solution that will help to mitigate those crashes. So the physical infrastructures, it's going to go from the existing camera that's already in the system, so there's no any added infrastructure there. We just need to create a software that will help us to detect the near miss. And once the near miss are detected, we then take those data. Basically, we are creating a data from an existing infrastructure, and then take those data to a database, and then do a crash insights. After the crash insights, there might be a feasibility, or there might be a lot of feasible solutions, and among them, maybe a geometric design. Maybe you need to work on a geometric design of intersection, or maybe the signal timing is bad. Maybe the permissive left turns is given to a intersection where the left turns or through volumes are very high. So those are the information, the insights should be generated by our city officials. And then I'm going to pass it to Slade.
So to capture the object in the video frame accurately and efficiently, there's a lot of AI models. The one we're using is the YOLO, you only look at once. It's a one-stage object detection algorithm for its high accuracy and better performance. So for the system overview, the AVAS utilizes YOLO Wi-Fi model for the object detections. The model itself, training on the cold data sets, can detect different traffic objects, including trucks, cars, bicycles, motorcycles, and pedestrians. And also, if there's any object not including the code data sets, the YOLO provide an easy way for training your new objects. Also, we developed a new graphic interface for using the AVAST, so the user do not need to start in a script from the terminal. You can just click a few buttons. Also, the AVAS can accept different kind of inputs, including the IP cameras, live videos, and also the pre-recorded video clips. There are 4 steps for starting the AVAS. The first step is define your detection zone. So the AVAS will allow user to draw the polygons on the frame of the videos to define your zone of interest. The next step is zone coupling or configuration. This is a critical step for allowing AVAS understanding the scenarios the user is trying to use. Do you want to detect a permissive left turn versus opposing through traffic, or pedestrian versus right turn traffic? So the third step is approaching speed configurations. The speed play a critical part in the near-miss detections. Since AVAS is purely software solutions, it's hard for us to get accurate speed. Instead of getting the accurate speed, we transfer the speed into the time gap traveling between the 2 zones. If you want a vehicle traveling 40 miles in the conflict zone, we transfer in 2 seconds gap between the gaps. The last step is with all the three steps configurations, the AVAS will push those configurations into the YOLO models. And in this step, the user can also select the model size for better detection, lower speed, or generate different kinds of report. Here are some examples of using the AVAS detecting traffic near misses. One of the near misses is crossing pedestrian with a permissive left turn, showing on the right figures. Also, the AVAS can also detect permissive left turn with opposing through traffic on the left figures. Right turn vehicle also with the pedestrian is also doable with different configuration of the zones. Here are more video clips of detecting near misses with AVAS. One of the benefits is AVAS can generate in 13-second video clips, 15 seconds before the incident and 15 seconds after the incident, to help the engineers better understand the cause of the near miss and also what's the impact of the near miss event. Some additional benefits of the AVAS is AVAS can also generate accurate traffic counts, whether the camera has high resolutions, medium resolution, or low resolutions. AVAS can all handle it. With the proper value and resolution, the accuracy can over 98%. And at last, AVAS will generate a report including the timestamp, zone name, total counts, and class-based counts. I will hand over to Imran to talk about stakeholders.
So the project will progress through multiple phases, with each phase associated with different stakeholders, starting from the UT Arlington, City of Arlington, also the TMC Arlington, and also the Action Lab students, and to analyze the videos and also to train the City of Arlington. Following that, they will train the third parties and they will maintain the software. And so here is the cost breakdown and the timeline. So the project will have 5 different phases, starting from the preparations, developments, implementations, testing and adjustment, and the deployment. So for the preparation to the implementation, we are anticipating for around 2 months. So we follow those timelines according to the US DOT research website of ITS deployment evaluations. And so in the for the testing and adjustment, we are anticipating for around 3 months. And for the deployment phase, with training staff and for the system operations and also the ongoing maintenance and accounting for some unexpected expenses, we are anticipating for around 24 months. So in the preparation phase, it would be to the connections between the City of Arlington and also the Action Lab, so training and fine-tuning the models with the relevant data. And in the development phase would be to developing a monitoring dashboard, and also in the implementations and in the testing phase to ensure the system reliability and the accuracy. So for the first stage 1 to 4, we are anticipating for around $100,000. And for the deployment phase, we are anticipating for around $50,000. So in total, $150,000. And for the anticipated impacts, because we are anticipating for different kind of impacts, starting from the operationals, environmental, mobility, safety, and the economic impacts, because building a system from the scratch would be really costly. However, to integrating the software with the existing cameras, we can reduce the cost and making it as a pretty cost-effective systems. And also, if we mitigate the crashes, then we can stop the stop-and-go situations that would improve the environmental efficiency, like fuel consumption and the emissions. And also it would smooth the traffic flow. And from the safety perspective, because the primary goal is to repurpose the cameras to identify near-miss events and to eliminate crashes. So by this way, we are prioritizing the life preservations, which align with the US DOT safe system approach, and to ensure eliminating crashes, which results in deaths or serious injuries. And this is a pretty cost-effective tool. So we have some limitations, like we are not providing any specific improvement measures. So therefore, but we are recommending to investigate the underlying causes of safety risk and also to recurring ongoing reassessments. So thank you so much. So this is all we had. So these are our references.
So again, excellent job, and we'll just open up to the judges for any questions.
I'm curious about the circumstance in which you tested this tool. Did you do different times of day, or did you consider different weather events, perhaps?
So far, we do test in different events. We record different video clips to test it, but in Texas, we don't have different weathers. It's all sunny days, so we're planning to do pictures.
I was wondering if you could do like a simulation of something, some weather events. But yes, you have a good location there.
Yeah. But we plan to use other video clips from other states to test the performance under different weathers. That's definitely where we plan to do it.
Great presentation. So, do your cameras need to be static, or do your cameras need to be static, or can you use cameras that actually can be used for surveillance?
So in this for our testings, we use both fixed cameras and also the cameras can move the angles.
Okay, thank you.
Thank you for your presentation. So I have a question. So you identified the problem, right? And then you chose software Avast. Did you research other options? Was that the best? What brought you to choose this particular one over any others if you've done that?
So our inspiration of developing Avast is from the YOLO model. It's a one-stage object detection model, which really provides the ability of detecting objects quickly and also accurately. So for the other products, most of the commercial solutions are combining cameras with other sensors, including radar or LiDAR, to detect your vehicle speed. So that is not an option for the city of Arlington. The city of Arlington has a lot of unused cameras. They want to utilize those cameras for detecting the near-miss events. So that's kind of how we start our developing our Avast software. And I hope that's answers your question.
Follow-up question on the sunny days. Did you test it also when it's dark outside, or does it work at nighttime?
For the nighttime, it's really depending on the resolution of the cameras. If the resolution camera is not so good, the headlight will blur the image, so you will not see anything from. It's hard for the algorithm to detect any objects. That's definitely a drawback from the video-based detections.
You might have mentioned this when I missed it, but in terms of the reliability of the software to detect near misses, did you find many false positives, or what are some of the factors that would improve the reliability of the?
So during the test, there's a lot of false positive, which is caused by the incorrect traveling gaps. Those gaps we're trying to using traveling gap within the zone to estimate the speed. That's kind of lead us generating a lot of false positive, because if you set the buffer too large, you have a lot of vehicles who actually wait there and then go, but trigger the events with opposite traffic. So that's one of the problem. We're definitely trying to do the calibration project for those time gaps for better performance.
So is there a way for the algorithm to learn based off of those near misses, or is there a way for the algorithm to learn over time based off that information, or how do you handle to reduce the false positives?
So for the near-miss detection, it's pure on our own logic. It's out of the YOLO model itself. The YOLO model itself only handles the object detections, and most likely it's going to be the hard-code input values we choose. So we're trying to do the calibration project to give the correct values or recommended values for the users to lower the false positive.
And I'll open it up again just to the audience. As I say that, I realize that one of the other student teams may ask a super difficult question, so please don't do that. Please identify yourself. But if anybody does have a question from the audience. Yeah, over here.
Have you used your system to make any changes, like design or engineering-wise, it's like you've seen something and then actually gone through a correction error?
That's definitely our next step. So far, City of Arlington trying to connect fiber with our lab, and with all the cameras in the City of Arlington, that will be our next step to detect near misses, see where it happened most, and trying to give recommendation for the layout changes, something like that.
Yeah.
At the same time, I want to add, so regarding the MOEs for the later of the project, we have not decided what exactly it's going to be. But in our previous research, we have worked with some multi-optimization, objective optimization, where we try to see worst of the worst scenario for emission, heartbreaks, and number stop. So that definitely it can be coupled with other data, external data, and the MOEs can be made more stronger.
And clarify, you're not with the student team?
No.
Okay. Awesome. We can't get a round of applause